So, good afternoon, everybody. Do you hear me well?
Yes, good afternoon, Yaron.
Okay, so thank you. So as Shai wrote to you, today we'll talk a little bit about Maumi, our Towerless project in Tanzania, which you all visited. And I'll show you how to design this Towerless project in EPAnet, or how to convert a conventional design to a Towerless design in the EPAnet. But before I will talk about the EPAnet, I want to show you this analytics view from the Inno app. I hope that all of you know this view already. And this is the water that we supplied during the past 1.5 months. You can see that I'm showing here the data starting from 22nd of June until the end of July, which was yesterday. So, as you all know, the project started operating around the middle of May when we had our seminar in Tanzania. And it was working well, but sometime around the beginning of June, we had like a malfunction in the pump, and it didn't supply like it's supposed to supply. So we had to replace it. And afterwards, starting from the end of June, around the 22nd of June, the system worked okay. So we didn't have any technical issues. But you can see that the consumption was very low, and I was worried that maybe something is not working well. So I asked the Tanzanian team, what's going on? Why we are not supplying water? This is not how it's supposed to work, the system. So they told me the system is working perfectly, but the community is not consuming the water. So I asked why they are not consuming the water, because they started charging from the water fee. And they started charging according to consumption, per consumption. For each bucket they fill, they have to pay. So this is why they consumed very less, around, you can see 3,000 liters per day, which is 2 liters per person per day, which is very low. So we said to ourselves that we can't evaluate if the system is working well if the community are not consuming the water, is not consuming the water. So we asked Larry and the country manager to go back to the village and do another sensitization, and actually to remove the water fee and stop charging the people for collecting water. So starting from like the first week of July, we removed the tariff, we removed the water fee, and you can see, and we asked her to do it for like the next 3 months so we can evaluate the system. And you can see how it affects the consumption of the water consumption of the community. It started to rise, and now it is stable around 20,000 liters per day. This is the average supply. So this is more or less 12 liters per person per day that we're supplying in Maumi, which is actually quite nice. And we see that the system is very stable for the last 3 weeks, and it is supplying very well. So this was for me an interesting lesson to see how the tariff is affecting the water consumption. Even though it is very low tariff, but for these poor people, it is, I assume it's a lot of money. So this is another consideration, not only the engineering, the design is playing a part here, but also economics and the social situation. And I think it's a lesson for us maybe to change the water fee system, not to charge per consumption, but to charge per month, per family or per housing unit. Maybe it will improve the situation. But for the moment, we're not charging for them for the water. So you can see that the supply is very good. So this is the evaluation, and now we can go back to the design.
Can you maybe just show everyone how you got to this page? Because I'm not sure everyone knows how to see this kind of data in the database. So it can be good to.
Okay. I usually access the database from my email because I get all these emails from the database. So I just open it.
I have it on my favorites bar, so I can just access it from the bar.
Yeah, this is a better way to do it. And so you have the menu here. So you have like the project list, and anyone can personalize his view with respect to the fields that you can see and can edit. And we have here the evaluation forms, and we have the analytics. So if we want to know how much water we supply in a specific project, we go to analytics. It's a little bit slow. And we get this view, and then we can choose the country, type of project, water, we're all water engineers, and the project name. So we can go and view another project, Manala. This is another project. You can see how much water we supplied during the last month. And if we want to see like today or yesterday or any other range of dates, we can choose it from here. Let's see how much. If we choose like a daily view, so we can see how much we supply every hour. So of course, at noon we supply the highest volume of water because the sun radiation is the highest. So this is a very typical supply curve to solar system that you can see here. Okay, so any questions so far? No. So let's go back to the design of Maumi. Let's start with the KMZ. Just to get a sense of the geography. The geography in Maumi is quite flat. It's not a hilly terrain, it is quite flat. And it is quite a long system. It is, we have a long branch supplying to all taps in the village. And the borehole is actually located here, and which is about 400 meters from this line. And as originally designed, the tower was located here. It was designed with a 10-meter tower that was located here. And now I'll go to the EPAnet, and you can see how it looks like in the EPAnet. So this is the original design. You can see that we have here a 10-meter tower. I can zoom in so you can see. We have here already, we can see the flow in liters per minute and the pressure at each node. And we can see that the pressure is okay. It is more than 3 meters in each node, in each tap stand as required. And I'll zoom in a little bit. And you can see that the 10-meter tower is located here. And we don't see the system connecting between the borehole to the tower. We usually don't require it. The calculation is done with the TDH Excel file that you all know. So it's not a requirement to include in the EPAnet the system between the borehole and the tank. So we can see that here we have a typical 10-meter tank with the maximum water level of 9 meters. above ground elevation, and ground elevation around in the tower area is 929 meters above sea level.
Okay. Yeah, Ron, I would just say that the minimum level here is a mistake. It should say 6.45, as we've mentioned many times, but yeah, this was an older one. Just
okay, correct. Yes, but it doesn't really matter. It's only 15 centimeters. So it's more or less, it's okay. So how do you convert this typical design, standard design to a towerless design? So let's do it together step by step. So the first thing that I have to do, let me show you the picture of the pump house so you can all remember what I'm talking about. You all remember this structure, correct? So here we have the borehole is located right over here behind this pump room, and we have here the ground level water tank, and inside the pump room we have the booster pump which supplied the water directly to the taps. So in this system, as you all remember, we don't have any elevated water tank. So let's go back to the EPAnet and do it step by step. And why is it important for us to learn? Because after this pilot, which seems to be successful, as you already saw, in the last 3 weeks, we supply like a stable quantity of water. We want to start piloting this type of projects also in other countries. I think that we will start maybe in Malawi, because Malawi is suffering from like high inflation and a very sharp increase in prices, and we are struggling to lower the prices. So we were thinking that this type of project might help us to reduce a little bit the project cost, the overall cost of the project, and also can speed the construction time. So we might have here 2 advantages. So the first thing that we have to do in order to convert this project to a towerless project is remove the tower, correct? So let's remove the tower, delete the tower. Now there is no tower. Now what I have to do is add the tank. The tank, which is located right next to the borehole. So as you remember in the KMZ, it was located somewhere around here. And now we'll add another node. And now I will add a booster pump, which is the suction of the pump is directly from the ground level tank. They will connect it to this node. And from this node, I will connect a line which will be connected directly to the water supply system. So this is very easy. Now we only have to fill in the relevant data in each one of the elements. So the length of the pipeline, of the distance between the borehole and this junction where the tank was, where the water tower was, is about 400 meters. The diameter is 63, but the inside diameter is 55. So this is the water pipe connecting the booster pump to the system. So we have this. The ground elevation near the borehole is about 927, if I'm not mistaken. Let's check in the KMZ. So yes, 927 around the borehole. So my memory is still working. And so this is the elevation of the node, which is located next to the pump. And I will have the same elevation, ground elevation for the water tank, 927. And the initial level, since it is located right above the ground, the initial level, I will say it will be half a meter. Okay, the maximum level, it doesn't really matter, but the minimum level is 0. The maximum level or 0.2 because there is a concrete floor over there. The maximum level, the height of the tank is about 2.5 meters. Diameter doesn't really matter, but let's say it's about 2 meters, okay? But the most important thing is that we are defining the elevation, the initial level and the minimum level correctly. So the ground elevation here is 927 and the initial level will be half a meter, meaning that the tank is full up to a height of half a meter. Okay, so it's almost empty. The last thing that we have to define is the characteristic of the pump. So in order for the pump to work in the EPAnet, we need to define a pump curve. In the pump curve, we define the working points of the pump. So let's, if you can see, let me just zoom in a little bit, that we supplied from the tank about 80 liters per minute. We supply 10 for this junction and 70 towards the system. So it's together about 80 liters per minute. So this is what we would like the pump to supply, 80 liters per minute. Okay, let's go back to the pump. So here in the data browser, I go to curves. I have to define the pump curve and I click here on add. So I'm adding a pump curve. And in the pump curve, I will define the working point of the pump. So the flow will be 80 because we want the pump to supply 80 liters per minute. But what is the head? So let's see what is the required head. How can we evaluate it? It doesn't have to be very accurate, but it has to be estimated or calculated upfront. So how can we do it? You all remember that the tank was somewhere around here, and the ground elevation at this point is about 230 meters above sea level, which is 3 meters higher than the borehole. So we have a 3 meter elevation difference between the pump room and this point. And at this point, we had an elevation head of the tank of about 9 meters when the tank is full. So altogether, it's about 12 meters. 9 meters plus 3 is about 12 meters. Now I can estimate that we have here head loss of about another 3 meters. So altogether, we require that the pump will supply 15 meters head. 3 meters for the elevation difference, 9 meters for the elevation head of the tank that we had here in the original design, and another 3 meters for the head loss. So altogether, it's about 15 meters. So let's go back to our curve and edit the curve. So we want a flow of 80 and the head of 15 meters. So the EPAnet is generating automatically this pump curve according to this working point that I want the pump to work. So I press OK, and I think now everything is ready. So I run the model, unsuccessful. What happened? I didn't insert the number of the curve. It has to be 1. Okay, this is the name of the pump curve that I just defined. So now it's supposed to work. Run is successful, and we have here towerless design, and we can see that the pressure in all the distribution points in all tap stands is okay. It's above 3 meters. So this is about it. Any questions?
Yes, Yaron, there was a question here about the pressures. The pressures seemed similar to when there was a tank, when there was an elevated tank with a tower. So the pressures that we saw now, can you explain again, what are those pressures? On the taps, I mean, the pressures on the taps.
So can you repeat the question, because I'm not sure I understood what the question is.
Yes, the pressures that we saw now in the taps, where is that pressure coming from?
It's coming from the pump. You can see if I will double click the pump, you can see here that it is supplying 80 liters per minute with a TDH of 15 meters. So this is the result already.
Okay, so it's basically what we were seeing in the original EPAnet was all of the pressures at the taps from the gravity pressure coming from the tower. Exactly. And now what we're seeing is the pressure coming only from the booster pump, which is set at a fixed rate of 15 meters or 1.5 bars. Yeah.
Yes. Let me just save it in another name so we can go back to the original design. So let's open the original design. So we'll just make the font larger. So it will be easy to see. So this is the original design. And we can see that, let's take, for example, DP3, okay, this one. You can see that in the original design, we have a pressure of about 5.5 meters. Why is that? Because this is worst case scenario. The tank is not completely full, okay? The initial level is 6.6, but I wanted to give a little bit more pressure. So I wanted to simulate a situation when the tank is full. So if the initial level will be 9 and not 6.6, when I run it again, we have now a pressure of about 8 meters, which is similar to the pressure that we received in the towerless design. Here it's a little bit more, but it is quite similar.
I think that's part of one of the advantages of using the booster pump, that we're not so relied on the water level in the tank, because the booster pump will give us pressure all the time, straight pressure. And then we can model it to be whatever we want. And with this, the changes of 3 meters here or there do not change the pump so much. So it doesn't make us go, we don't need to get a larger pump just to get that extra 3 meters of head. So that's the big advantage that we can have with the pump. beside the fact that we can reach higher elevations. So yeah, so I think that's the point, and it's a good question.
Okay, so you have any questions?
Yes, I have a question.
William, unmute yourself.
Yeah. I have a question. Good morning, everyone. Yeah, when we simulate the system with a form, something that always goes to the past, but I was observing that the demand on the tap system, I don't know if you can check the demand on the tap stand. It seems like when we simulate it, the demand is not equal to what we are designing at that time. Don't know if I'm mistaken.
It's really hard to hear you. Maybe you have headphones or something, because we can't really hear you.
Hello.
This is better. Now we can't hear you at all. Still can't hear you.
Maybe you can write in the chat. Yeah.
You can also try to write in the chat. So Yaron, I had a question in the meanwhile. When you took the head losses, why did you take 3 meters to be the head loss?
Why into account 3 meter head loss?
Why 3 meters? Why not 5? Why not 10? Why not 2?
Okay, because we have here a 63 millimeter pipe, and it has to convey 80 liters per minute. Okay, so if we see the unit head loss in this pipe is 7.3 meters per kilometer. So for 400 meters, it will be about 3 meters. Okay, it's not an exact calculation, but it is close enough.
Great, thank you. So that's the pipe going from the booster to the first node of the system, right?
Say again.
So this pipe you're showing the head losses for, pipe PL1, is that the pipe going from the booster to the first node of the system?
Yeah,
this one, okay.
This is this one connecting the booster to the point where the tower was supposed to be.
Okay, there was a question in the chat, but Pascal raised his hand first. Ah, here is William with him. We still can't hear you. We still can't hear what you're saying. Okay, now we hear you.
My question was concerning the demand on the tap stand, the needs of water on the tap stand. Because I don't know, maybe it's a mistake for my part, because sometimes when I'm simulating a system with a pump, it seems that the demand on the tap stand are changing. It's not the same as we already put. Everything is changing. The system is not equilibrated. Yeah. Maybe a small bit to. Maybe you can check on the demand. Maybe I'm mistaken something.
William, if I understand correctly, what you wanted to say is that here in the model, we define the demand of 10 liters per minute for a tap stand.
Yes.
But the actual demand is changing. It is not constant.
That's what I'm saying.
So you're correct. This is a simplified way to model like a water supply network. But it doesn't actually work like this, because the flow that is coming out of the tap is pressure dependent. if the pressure is high, we'll have more flow.
Okay.
Right? Correct. If the pressure is low, the flow will be lower from the tap. So we can simulate a system with demand nodes that are like pressure dependent.
Yeah.
It's a more complex way to simulate the system. But I think the simplified way is usually okay. It's usually work fine, and according to the designs that we approved so far, and in the last 8 months that I'm working for IA, we didn't have any system that there was a problem with the tap that didn't receive water.
Okay.
Except for one project in Tanzania when we had to regulate the flow, and then everything was okay there also. So usually it's okay. It's a simplified.
On this case, how can, if you are receiving, maybe I say something, if you are receiving the net file from the contractor, how can we check to be sure that the demand on the tap stand are good now?
How can you check that the demand in the tap stand is
good? Because normally when we are checking, you are supposed to, if you are checking the case where you are writing there to have 80 liters per minute.
So you can open all taps in the system, and if you want to test one tap, you go there with a jerry can and you fill the jerry can. And
I'm talking on the EPAnet, when we are receiving the net frame from the contractors, for example.
Okay.
How can, because if you are supposed to, if you are designing something to obtain 80 liters per minute, and at the end of the day, is it possible to have laser on that case or more than 80 liters per minute? How can we be sure that you have something which is more accurate or good? That
So
we can go ahead
I can tell you what is our requirement, and we're gonna have it in the water manual. The new version is coming out really, really soon. Hopefully next week you're all gonna get the new version. And I think we're gonna put a step-by-step EPAnet design so the contractor can have it with them. And what we usually do in other countries, they just take the sustainable yield from the pumping test and they divide it by all the taps.
Yep.
And that way, so if you see that the total demand in all the system is the same as the sustainable yield, then you know that it's fine. You won't know exactly what would be the flow in each tap.
Yeah.
You can also use the how you do it usually, if I remember correctly, you do some sort of calculation based on how many people live around the tap, and you give more to one tap and less to the tap that has less people. I don't know if that's exactly how you do it, but I see that sometimes you have different demands in each tap.
Yeah, we have different taps. Yeah, we are working with per quarter. We are distributing water per quarter. That's why we have a different demand per taps. It's not something which is similar. And at the end of the day, the quarter where the population is higher than the other one, we will see that the diameters of the pipes is more bigger because they need more water and more pressure. Yeah. And the quarter where there's not a lot of people there, they will have the demand of water there will be lesser because we are when we are taking the size of the population, we are going to the field to do some repartition of the population per quarter. And we observe we are taking all those information, we are coming back to the office and manage everything then. Yeah. But I'm not sure that I was having an answer about my question.
Yeah, William, you asked, I don't know, a simple question which just doesn't have a simple answer.
Yaron, let me just come in, if you will allow me. William, I want to say that in Innovation Africa, we really want to keep things simple. We have enough work. We have a lot of goals and a lot of projects to accomplish. What you need to do is just what Shai explained. We want to use the simplified approach. It's not exactly what happens in reality, but it's a simplified approach that works for us. And you want to take the borehole yield, let's say it's 1 liter per second, times 60 minutes, so it will be 60 liters per minute. And you take those 60 liters per minute, you divide it by the number of taps. Let's say there are 10 taps, so you have 6 liters per minute in each of the 10 taps, and that's it. We want to use a simplified approach that will have the same demand at each tap. It will make your life easier, it will make the contractor's life easier, and it will make our life easier when checking it. We don't want to overcomplicate things, so I think we'll stick to that for now.
But I'm willing to take the challenge and and maybe show you in one of the next sessions that we will have how to model a system with a demand node nodes that are dependent in the pressure in the system. Okay, so
Okay.
it will be also a good exercise for me as well. So.
Okay, but William, do you feel like you got the answer? Like, do you feel you understand what to do with the contractors moving forward when you get designs from them?
Yeah. Yeah, you understand very well what to do to move forward. But my question was concerned, how can we check in the case that we have a pump or a bus stop on the system that we are designing? How can we check to be sure that now we have a good demand? Because on the case that we have a pump, the demand that changed on the tap stand is not the same thing on the net file. It's not the same. And when we have the result, how can we check to be sure that we have a good result? If you have the demand on the tap stand lesser or lower than what we are lower and lesser than the 80 liters per minute, is it good, or we're supposed to have something over than 80 liters per minute when we are simulated with the pump?
I think, William, of course, in each and every tap stand, assuming that the water tank is full and all taps are open, okay, in a specific system. So, of course, we won't have the same exact flow rate in each and every tap. It will change according to the pressure in the system. So, in taps that have better pressure, the flow rate will be a little bit higher. In taps with low pressure, the flow will be a little bit lower. I think that the main question here is it enough to supply the people without queuing, without them making them stand in queue in the tap for like half an hour, okay? If the flow rate is so low, they will queue in the tap. If the flow rate is okay, so we won't have any queue in the tap. So this is the question.
Yaron, regarding that, I think our bare minimum should be 6 liters per minute, because that's about 3 minutes to fill a 20-liter jerry can. We don't want it taking more than 3 minutes. So I think about 6 should be the minimum, but correct.
Yeah, I agree. And I think it is, you should ask this question yourself when you're in the field visiting systems, and see if people are queuing around tap stands. Try to see if the flow rate there is sufficient or not. And maybe we can learn something from this in headquarters, and then change our design criteria accordingly. Okay, but for the moment, we didn't have any kind of these challenges. So I think that with this simplified way, I think we are doing okay so far. But if you see that in some systems that you visit, that people are queuing around the tap because the flow rate is not good enough, so try to ask yourself, what's the problem? Go back to the original design and see if something is not okay there. So this is also my recommendation to you. But in one of our next meetings, I will show you how to model this demand, which is dependent on pressure. Okay.
Yaron, there was another question. here regarding how to create the booster. Let's say we don't have the original design with the tower, and we just have a system and we want to put a booster, and we want to know how much is the TDH, or how much is the head we're going to give the pump. So how would you determine, well, what can you give the people here some guidance on how they can determine the head of the pump if they don't have a system like Maumi where they already have the original gravitational design?
So I think you go to the highest point which you want to supply water to. This is like the critical node, the critical demand node, which will be the highest point in the village. And you go there and I want to give this tap stand, I want to supply it with at least 5 meters of pressure, and then go back and see what is the elevation difference between this tap stand and the borehole. So you add this one and then you can try to estimate the head loss along the way from the borehole to this tap stand. So when you add these three items one another, then you get approximately the desired TDH of the pump.
And you can play around with it. If you see that you don't receive good pressures in the taps, you just go back to the pump curve that you just inserted, and you change the total head that you have there. You can change it to whatever you want and see how it affects the system. Now, if you change it to 20 and you press run, we can see how the pressure will change. You see now everything went up by 5 meters because he increased the total head. So you can always play around with it until you reach the desired head that you want. And as we start to do more and more pilots like this, we'll get to be more familiar with the kind of booster pumps that we have in the market. And we will know, like, I think we will have like a specific booster pump that we will always use, and we will know the range that it fits to.
Any more questions? Okay, so let's talk about filters for a few minutes. Okay, because a few weeks ago we